In this chapter, I want to show you how to use raster libraries for data analysis, for clustering statistics, gathering some statistics, and applying some aggregation. The main libraries that we're using are NDArray, LinFi, and Polars. And NDArray is a library for numerical operations, and you can think of it as NumPy in Python, and it provides multi-dimensional arrays. LinFi is a basic machine learning library. It offers a variety of algorithms and tools for tasks such as classification, regression, clustering. In this case, we're using k-means clustering to group earthquakes based on their characteristics. And then at the end, we've got Polars. It's a high-performance data frame library, and it's similar to Pandas, but optimized for speed and memory efficiency. And we can really handle large data sets more effectively if we use Polars and Rust. First, we get our data ready for clustering, and we use the NDArray library. We need to transform the earthquake event data into a format that's compatible with clustering algorithms. We do this by extracting longitude and latitude from each event and creating a vector, a list of these coordinate pairs. Here, event.coordinates.line and event.coordinates.lat. And then this vector is then converted into an NDArray array2 object, which is a two-dimensional array, specifically designed for numerical operations. Each row in this array represents a single earthquake. And then two columns hold the longitude and latitude value, respectively. So we've got first zeros with this length and two columns. And then we say, okay, the first column is longitude, the second column is latitude. And this 2D of earthquake coordinates as the input will provide to the k-means clustering algorithm. So we're looking at the function cluster earthquake events, which gives us a structured way to group our earthquake data into clusters based on their geographic locations, longitude and latitude. These clusters then can be used for further analysis, such as identifying earthquake hotspots or regions with similar patterns of seismic activities. Let's see how we're doing this. The first thing we do, as you've seen this function, we prepare the data. So we transform it from the earthquake event struct to a format that is suitable for clustering. And then next one, we are going to do the model fitting. So here we create and train a k-means clustering model with the desired number of clusters. And we fit the model to our observations. And we prepare our observations as 2D arrays before, and that's lines. And then once the model is trained, we obtain cluster assignments for each earthquake event, which tells us which cluster each earthquake belongs to based on the model's analysis of the data in these lines. And then we have the initialization that will create a vector called clusters to store the information about each cluster. Each cluster will hold the earthquake events assigned to it and it's calculated centroid. Centroid is important. And that happens here. And then after the initialization, we iterate through our original events list and the corresponding cluster assignments. For each earthquake, we'll push it into the appropriate cluster within the cluster's vector. And the next step is, after all earthquakes have been assigned, we calculate the centroid, which is the average longitude and latitude. And that centroid represents the central point of the cluster. And here we can return it. We can return the clusters as a vector, which now contains the complete information about each cluster, including the earthquake events belonging to and the cluster's centroid. Here's a recap. We convert the observations from a vector to an NDArray array2. We apply a k-means algorithm, which comes from the LinFi library, and we group earthquakes based on their proximity. We then determine the optimal centroids. We initialize empty earthquake cluster instances. We'll see this struct very soon. And then we assign earthquake events to the corresponding clusters. We also calculate the centroid for each cluster by averaging the longitude and latitude of the earthquakes. And then we return this vector earthquake cluster, this one, where each cluster contains its member earthquakes and centroid. So the earthquake cluster is a struct and is designed to store information about each cluster of earthquakes after the clustering process. This struct represents a single cluster of earthquakes and it has two main fields. It's got events and centroid. And events is a vector of earthquake event structs. We've seen earthquake event multiple times throughout the course. It stores all the individual earthquake events that have been grouped together into this particular cluster based on their proximity to each other. And then we've got the centroid, which is a tuple with two F64 values. It's floating point representing the longitude and latitude, as you know, the coordinates of the cluster centroid. And the centroid is defined as the average location of the earthquakes within the cluster, effectively serving as its central point. The other important structure that we define here is metric statistics, and which is to hold statistical information about a single metric, such as the depth or magnitude of earthquake. The minimum is a minimum value observed for that metric, maximum value, and average value. And this is cluster statistics actually aggregates statistical information for an entire earthquake cluster. And it includes the following: centroid, the coordinates, as you know, depth stats, an instance of metric statistics summarizing the depths of earthquakes in the cluster. Magnitude stats, an instance of metric statistics summarizing the magnitude of earthquakes in the cluster. And duration, which is an optional value representing the time elapsed since the last significant earthquake in the cluster. Talk a lot about the statistical analysis, cluster statistics, and the centroid, and the statistics of depth and magnitude and duration. But the thing is, I forgot to go to the next slide. So this is what the struct looks like. We are now up to calculate cluster statistics async. So it's an asynchronous function. We've done all the clustering and want to calculate the statistics for each cluster to represent it as instances of cluster statistics that we just saw in the previous slide. So the code performs the following actions. First of all, data extraction for depth data and magnitude data, which is from the earthquake event instances, as you can see. And we use a map because we want to turn a collection to a collection, or a collection to a vector. So we get the magnitude, and in the other case, we get the depths from the event, and then we collect them as vectors. Now going forward to this calculation, which is happening using the Tokyo join macro, which is the concurrent calculation of depths and magnitude statistics, and this is followed by returning the stats in a tuple. To calculate all cluster statistics, async takes a vector of earthquake cluster objects as input and returns a vector of cluster statistics objects containing the calculated statistics for each cluster. Here's how we do it. So first we create the tasks like this. And then in this creation, we iterate through the clusters, the vector of clusters, and we create asynchronous tasks for each cluster. The clone method is used to create copies of the centroid and cluster data for each task, which is important because Russell's ownership rules wouldn't allow us to move the original data into multiple asynchronous tasks. So therefore, we have to use a clone here. The next step is async move, and you can see it here. And the move keyword transfers ownership of the variables captured by the block, in this case, cluster clone and centroid, from the surrounding scope into the block. So we've got this block, and we have to move the ownership. So the move keyword, we know what it does, but what it means is the async block becomes the sole owner of these variables, ensuring that it lives as long as the task needs them, even if the original cluster is dropped or modified elsewhere. And inside each task, we calculate the duration task and the depths stats and magnitude stats using the calculate cluster statistics async function, which we saw in a previous slide. The await operator is used to wait for the results of this asynchronous calculations to be done. That's why we've got the await function here. And then each task produces a cluster statistics struct containing the calculated statistics for that cluster. So this part is the return of each task. Then we have the join all here, try join all. And this one is a function that is used to wait for all the asynchronous tasks to complete. And then this function collects the results of all the tasks into a single result value. And then we have to handle the results, and we do that part here. In the last two slides, we are going to use the library polars and want to perform some temporal analysis in order to group earthquake data by year and month, and we then calculate the counts of the number of earthquake events for each year and month. In order to achieve this, we've got the events to data frame. First, we have to create a data frame, a Apollo's data frame from the earthquake events. And in order to do this, we map over the list of earthquake events to extract relevant fields, timestamps, magnitudes, etc. into separate vectors. The collect step gathers these mapped values into vectors, which are then used to create series for the data frame. So these are the series. For each column, we have the series, and then the overall data frame is actually calculated from those series as its columns. Then the next one in this function, the next function, which is the temporal analysis, what we do is a cloning and lazy evaluation. In temporal analysis, we clone the original data frame to avoid directly modifying the original data, and then we use lazy evaluation for efficient and deferred execution, which allows us to chain operations like data time conversion, feature extraction, and grouping without immediate computation. So we do all of that, and sometimes we end up with a smaller data frame. So at the end, when we actually execute it, we execute it on a smaller data frame. That's why we always do this lazy evaluation. Now I'm going to talk about the parsing errors. So if we go to this part, the first line, you can see that both functions return a result data frame and Apollo's error. This error handling mechanism ensures that if something goes wrong, like an issue with the data conversion or grouping, Apollo's error is returned. So that makes the calling code to handle the error gracefully rather than causing a runtime panic. And now we can achieve what we wanted, and that was grouping by months and year, months, and counting the number of magnitudes for that particular year and months.